Okay, follow-up video on the basics of the advanced multiplying rule, because there's an advanced multiplying rule also. So it says find. So this is kind of sneak previewing. It says find these probabilities. What's the probability of graduate student? So graduate student is 33%. So probability of graduate is 33%. Notice I write as a decimal because I'll multiply them in a second. I want the decimal there. Probability of being a Mac user is 60%. And so the probability of being a graduate student and a Mac user would just be 0.33 times 0.60, which is, handy dandy calculator, 0.33 times 0.60 is 0.198, which is 0.198. So that's probability of graduate student and Mac user. But wait a minute, graduate student and Mac user, I'm seeing on the chart that it's 0.23. There's 23% of graduate students, 23% of all the students, these are all the students right here, and then they get totaled up on the outside, that 23 out of the 100 are graduate students who are Mac users. But when I multiply the two probabilities together, I get 0.198. So it looks like the multiplication formula doesn't work. And so the answer, does the probability of G and M equal the probability of G times the probability of M? And the answer is sometimes. And that would be like your sneak preview, like, oh, the multiplication formula doesn't exactly work either. So we've got just like before, there's a reason why. And we're going to go through the reason why, and then we'll see how to modify the formula in order to make it something that actually works. Okay? So first, let's just think about the reason why. Well, if we look at it, like overall, you're right that 33% of the students are graduates. But then when I look at Mac using and graduates, it's like, wow, graduate and 60% of students use Macs. But when I look at the graduate students, it's like, whoa, okay, that's a lot more than 60% of the graduate students are using Macs. Like once I know I'm talking about graduate students, that 60% Mac rate doesn't seem like it's right because there's 23 out of 33. It's actually, it's higher. It's not a ton higher, but it's like 70%. 70% of the graduate students are using Macs. So even though 60% of the students overall use Macs, if we're talking about graduate students, and we are in this problem, then the percent is a lot higher. And so it's like, oh, like I use the number 60% here for the rate of using Macs. But if we're talking graduate students, that number isn't right anymore. All right, so the easy version of the multiplication rule for easy problems is the probability of A and B is the probability of A times the probability of B. That's the easy version. Totally works in certain circumstances. If you flip a coin 4 times in a row, what's the probability they're all heads? It's 1/2 to the 4th. That totally works. That hasn't changed. And we're gonna. I have an example here that I'm not going to go through. I do it if we're in class. Well, okay, I will do it really fast. So I say the probability of randomly choosing a student in the AP Stats classroom who has glasses or contacts. Maybe we've got like about 5 out of 26. I'm included in this. And how many people are over 6 feet tall? Maybe that's like 7 out of 26. And what's probably they're born out of the state? I'm making up the number. Maybe 4 out of the 26 were. And what's probably the person has facial hair? Okay, now I'm trying to imagine the class and saying, okay, does anyone have a beard or a mustache in class? Not really sure. That's kind of tricky. I'm going to give room for one. I apologize if I'm forgetting an obvious person who's got a beard out to here. So 2 out of 26. And so if I try to use the multiplication rule and said, what's the probability of picking a per person in the room and saying they have glasses and they're over 6 feet tall and they're born out of state and they have facial hair, you'd think that it was 5 out of 26 times 7 out of 26 times 4 out of 26 times 2 out of 26. But really the answer is it's 1 out of 26. It's me, right? Like, so, and that's a lot bigger than multiplying all these together. That's going to be a tiny answer if I do that. So we got an issue. Like once we said the person has glasses or contacts, then the probability of picking one of them and having them being over 6 feet tall, that's going to be a lot bigger than this because there's just 5 of us that we're talking about. Like once we've gone through the first hurdle here, once we've said this is true, the person has glasses or contacts, then the probability of them being over 6 feet tall is actually changed because we're only talking about the glasses people. And once we're only talking about people with glasses and people who are over 6 feet tall, we might be talking about 1 or 2 people at that point. And the probability they're born out of state is going to be pretty good because I was born out of state. I was born out in California. And then if we say, well, what if they have facial hair? It's like, well, yeah, they have facial hair because we're talking about that dude there. We're talking about me. And so the probabilities are going to change because once you know that the early conditions are true, then the probability of the later conditions being true is going to go up. So here's what the more refined probability rule is. The probability of A and B is equal to the probability of A times the probability of B. That's the easy one, as long as A and B are independent. Meaning that the probability of either one of them, but I'm just going to say probability of B is the same. I'm listing that one just because it's second, so it makes a little more sense conceptually, is the same no matter what happens with A. So the probability of the second thing being true is totally the same no matter what happened when the first one happened. If that's true, then A and B, if A and B are independent, then the probability of A and B is the probability of A times the probability of B. And that's why we could use it with the coin. Because the coin, like the probability of getting heads and heads, the probability of getting that second heads is exactly the same whether or not the first one was heads. What happened with the first one has no bearing on the probability of the second one. And so we could just multiply them. But if the probability of A and B, if A and B are not independent, the probability of this happening depends on what happens with the first one, then we have a more refined formula. It's the probability, that was kind of weird. Get rid of that. The probability of A and B is the probability of A times the probability of B, given that A has occurred. So, for example, the probability of the person, what were my first two, having glasses and then being over 6 feet tall is the probability of someone having glasses times the probability of B, given that you know that the person has glasses. So you have to update it to reflect the fact that, we're just talking about the people who have glasses now. There's a notation way to write this, and the notation way to write this is that it's the probability of B given A. So that bar there means given that. And then A is true. So the probability of A and B is the probability of A times the probability of B under the assumption that A is true. We're going to show you a bunch of examples of this in just a little bit. Okay? We're not going to, we'll keep this one. So, and I'm going to have to make up the numbers here, like before. So the probability of glasses, we said what that was. Probability of glasses, we said it was 5 out of 26 with my made up number. And then we say, what's the probability of them being over 6 feet tall, given that they have glasses? So this means that you know the person has glasses. So all the people who don't have glasses, you can push them aside, and leave them off to the side and say, of the people who have glasses, what's the probability that that person is over 6 feet tall? And maybe, so there's 5 of us who have glasses. So maybe it's 2 out of 5. Maybe there's one other person, and maybe there's more. I'm making up the numbers. And then you say, what's the probability they were born out of state? Now you know that they're over 6 feet tall, and you know they have glasses. So all the people who aren't over 6 feet tall and don't have glasses, we push them all aside, no offense. And we say, just of the people, I'm sorry, I might have said that wrong. Just the people who are 6 feet tall and have glasses, we put them together and say, what's the probability one of them was born out of state? So now we know there's only 2 of us left who have glasses and are over 6 feet tall. And maybe the other person was born out of state. And so maybe it's 2 out of 2. Like both of us were born out of state. And they say, okay, given that all those things are true, so we're still just talking to those 2 people, what's the probability of the person having facial hair? And let's just assume that I do and they don't. So the probability of glasses and out of state and 6 feet tall and facial hair is the probability of glasses times the probability of being over 6 feet tall of the people who have glasses times the probability of being born out of state, given all those things are true, and then times the probability of having facial hair of the people who have all those things true. And when you multiply those across, you get the 1 out of 26 we'd expect. And we're going to see a bunch of examples of this. And it's really going to come into play on Friday. But I want to just give you that idea of why we're doing this formula and to introduce this advanced formula. On the formula sheet, it actually doesn't write the formula the way we wrote it here. We said probability of A and B is the probability of A times the probability of B under the assumption that A is true. The way the formula appears in on the formula sheet is it says the probability of A given B is the probability of A and B divided by the probability of B. Now you might notice that this has the same stuff. Remember, this here is just and. So it's like, oh, we know that. And so all they did was they divided one thing over to the other side. They've got it reversed, but it doesn't really matter because A and B is commutative. It can go either way. So if you want to, you could multiply the probability of B up and say this is the same as the probability of A and B is the probability of B times the probability of A given B. And this is the same as the one we had earlier. We wrote it this way instead because A and B is commutative. It can go either way. You can also say it's the probability of A times the probability of B given that you know A occurred. These are the same thing. Now, I just like to write it the other way first because I feel like I can explain it better that way. So we'll talk more about the examples of using this next class. We'll look at superpowers and goals in life. We'll talk about independence and have a definition for independence. We'll see that in just a little bit. And then we're also going to see a thing called probability trees. So if you look at chapter 14, it's kind of a bunch of examples. We're going to talk about cancer. And then we'll see if we get to the other stuff. But that's all for next class. All I want to do is to introduce to you the general or rule, and then introduce to you the general and rule and why we have it. And next class, we'll get into the applications of the and rule. Okay. Those are the videos. You've got some problems that are assigned in the AP Stats book, so you'll have to go there to do those. And we'll see you on Friday.